Like this?
Yeah, I think so. Can you hear us? Hello, hello.
Yes, we
Yeah.
can hear you.
Perfect. Okay.
Good.
Thanks.
Good. So we can hear.
Good. Okay, so I think we are done. So it's an honor to have today with us Per Stenstrom from Chalmers University. Per doesn't need any introduction. All of you already know Per. He's one of the most successful computer architects here in Europe, and he's a good friend of BSc and UPC because he has been collaborating with us even before BSc existed. Per is an expert on cache hierarchies, coherence, replacement policies, compression, many very important topics for all of us. And today he will be explaining, well, you will be covering basically your work on these topics in the last years. So you have 45 minutes, more or less, plus 15 minutes for questions.
Good.
So the floor is yours.
Thank you very much, Mikael, for the introduction. Yeah, I've been around in the field of computer architecture for quite some time. In fact, it was 6 years ago as I got my PhD degree from Lund University at the time. And of course, I've managed to, my key focus ever since I was a PhD student has been memory systems, high performance memory systems. I've worked on many topics, as we can point it out, but certainly the topic that I've probably spent most of the time on is applying compression to memory hierarchies. So this talk is going to be kind of an overview. I'm going to do some sampling of some papers over the years that we have looked at that I'm quite proud of. But I wanted to start with saying, how did I end up doing research on compression techniques? These words.
I'm gonna go here. Oops.
Okay, and now click on the slide again.
And now maybe
you can try.
Work also with the presenter.
And now you can try with the presenter.
Presenter.
With the pointer.
It seems to work. Okay.
Okay, so how did it start? How did I get interested in compression techniques? Well, it's a kind of a cute story. So my daughter, who is today turning 30, at the time I started to work on compression, she was just a few years old, and as a parent, you read fairy tales for your kid, for the kid to sleep. And I was very eager to get her to sleep because then I could continue to research, right? So I wanted to run to my computer and start working again. But not losing any seconds while I was waiting for her to sleep, I was starting to think, what if we could compress data in the memory hierarchy very efficiently? That would certainly create a lot of values. You could shrink the amount of memory you need. That means that you can increase the memory capacity, build more cost-efficient memory systems, okay? And a lot of other things that we are going to talk about. So when she started to sleep, I went to my computer and started to see what has been done in this area. I want to read up on state of the art immediately. And that was not much. In fact, IBM had published a paper in HPCA on what it was called MXT, the memory expansion technology, MXT. But their compression solution was based on live sample compression, was very slow. So they had to use a huge cache in front of it to hide the latency of doing compression. So I said, there's certainly room for a lot of work. So I got super excited about that. So what we're going to do is that I'm first going to give you some motivation why this is an important topic. the case for compression in memory hierarchies. And then I'm going to present kind of a cute limit study of what compression could offer. And then we're going to look at sampling of contributions we have done over the past 10 years. And this has all been done at the Chalmers University of Technology. But since we did a lot of progress on this topic, we saw as I indicated, the value of doing compression is being more efficient and cost efficient, you could say, memory system. So there's certainly a commercial value in it. And so I'm going to talk also a little bit about ZeroPoint Technologies, which I'm very proud of, one of the companies I've founded, and what we have been doing, what we are doing there. Okay? Before I conclude. Can I get rid of that thing?
Yeah.
I can't. Okay. And I didn't do anything bad now. I'm still.
Let me hide this. Let me.
Excellent. I think that will do it very well. Okay, so applying compression in the memory hierarchy, what could we actually gain from that? Well, first of all, we can improve the utilization of both caches and memory. In fact, this is applicable to the entire memory hierarchy. By actually compressing the data, you can buy yourself bigger caches and memory. We're going to see how that is done. And if you buy yourself a bigger L3 cache, then of course you will cut down on the miss rate. There is this rule of thumb that if you double the size of the cache, then you cut the miss rate by square root of 2. It's a rule of thumb. It's not exact, but it's actually give you some idea, you know, how much that matters. And this matters a lot, especially now with when Moore's law is running out of steam. Then it's not as easy to invest in bigger caches, but with compression you can buy yourself. We're going to see what happens if we apply compression to that. But there are other things too. You can, if you compress data in the memory, then you can bring in data in a compressed fashion, and that will actually improve the effective bandwidth between the CPU and the memory, okay? And on top of that, what especially data center hyperscalers are worried about is total cost of ownership, and especially operating costs. And memory consumes a lot of energy. So by cutting down, well, in fact, so by using compression, what we can do is to reduce the capital expenses by offering low cost of memory, but also operating costs by improving on energy efficiency, because you can bring in data in a compressed mode. So there are a lot of good things. I hope you're motivated by now. So let's actually look at the first study that we did with one of my former PhD students, Angelos Aroulakis, was to look at a limit study of what compression could build us. So let's actually have a look at that. We are all we know about reference locality, which comes in two flavors: spatial reference locality and temporal reference locality. What people are not, well, spatial, of course, means that if you access a certain location, very likely to access a nearby location. And with temporal locality, it's the fact that there is a high likelihood that you reference the same location again. But what people maybe not think about so much is that this also applies, what we have seen experimentally, to value locality, meaning that what temporal value would be that if you access a certain value, it's very likely that you will access the same value again. And the reason for that is that it turns out that values are replicated in memory quite a bit. 0 is a good example. Of course, if you have zeroed out the whole page, then all the values will be 0. There will be huge amount of temporal value locality. But it also turns out that there is a lot of spatial value locality. What does that mean? Well, that memory is filled up with numerically similar values. Since we are at Barcelona Supercomputing Center, where you, for example, do ocean simulations, if you measure the temperature at one point in the ocean and a temperature to a point nearby, then the temperature will be similar, right? It could actually be the same too. So spatial value locality is something that actually intrinsically applies to a lot of physical phenomena, okay? So that's what we have seen, and one can exploit that. So one experiment we did, this goes back quite a bit. So forget about the graph for a minute. I was very interested. This was the first assignment to the, at the time, new PhD student, Agnes Aronaki. So I said to him, think about that you have a cache, a hypothetical cache, where you can afford to only store each unique value once, okay? Then the question becomes, how much smaller could you make that cache? If it was smart enough. Let's not worry about how you build that cache. Let's just look at the effect it would have if you store each value once. So he went back to his desk, and I didn't see him for a while, so I thought he had, become sick or something. But he was really thinking about this problem a lot. And then he came back to my office. I have some data for you, and it was pretty much this graph. So what we have here is the classical diagram of the misses per kilo instruction as a function of the cache size, okay? And the green curve here shows, you could say, a conventional cache, where for this particular application, what we see is that the miss rate will at some point go down. At 2 megabytes, you can see there's a sudden drop in miss rate, okay? This is typically what happens if you do this kind of graphs. This is what you will see, of course. Now, the red curve here is what corresponds to what we call a value-aware cache. And here you can see that the drop in miss rate happens earlier. In fact, it happens at around 256 kilobytes instead of 2 megabytes. So if we take the compare 2 points on these two curves where they exhibit the same misses per kilo instruction, we can see that the size ratio is in fact 16 times. That will give you, an idea of the potential of doing compression if we were to do it with only storing a single value once. How you do that turns out to be very difficult. We played a little bit with that, but you get killed by metadata to figure out, to go to a table where you only have unique values, and you need metadata to point to essentially, and then most of the compression goes away. But we looked at, across, this is spec 2006, I think, some applications here. You can see that it was not only for that sample application, but for quite many of them, we get a compression factor of 28 on average. So it's a huge amount of, there's potential here to really use the caches or memory more efficiently. That is what we actually expect with accepting computer picture levels back in 2012. It's kind of an old paper. So armed with this motivation, we start to look at cache compression. And we were the first to use statistical based compression, entropy inquiry, to do compression. And with that, state of the art at that point in time was kind of simple compression techniques, pattern-based compression techniques that you could build very fast. You could make them compress and decompress really fast at the nanosecond rate, but they were not very efficient. Okay, we're going to look at what happens if you do statistical-based compression. So we focus here on the last level cache. That's where it makes sense. You still have applying compression to L1 and L2 is tough because you have to decompress the data when the process requests it, and the latency will end up on the critical memory access well. But with the L3 cache, if you're doing quite efficient compression and decompression, then you can probably afford. Okay. And the good thing is that we can expand the cache capacity, which is of course big. So that's the motivation. Okay, so what did this SC2 statistical cache compression do? Well, first of all, to map it into the at the time the state of the art techniques. So what we see here is the compression ratio and along the y-axis and the decompression latency in nanoseconds along the x-axis. Okay. So BDI stands for base delta immediate compression. It's a very simple compression technique where you use the first word in the cache flow to act as a base, and then you essentially store the differences with the other words with respect to that base. Okay, and that has a decompression latency that is just 1 and 2 nanoseconds for decompression and compression respectively. There was another scheme. FPC, frequent pattern compression, that also works on patterns, we could say, common patterns, and it could also do some compression, but not very efficiently, typically around 1.5. What we tried to achieve here was to add a little bit more latency, but to the gain of having higher compression rate. But still, you have to worry about the decompression latency, especially if you're doing cache compression, because it's not insensitive to the decompression rate. Okay. So when you do statistical compression, what you need to do is that you need to gather information about the relative frequency of different values. We're going to see how that works. Then we do code generation based on these value frequencies, and we used Huffman. Okay. You may ask what happens if the value statistics distribution shape. You have to shape the Huffman coding. We're going to go back to that in a while. Okay. To do cache compression in general, it's not, there are a couple of challenges you need to address, because now the plot has variable size. So it's much about how you actually manage that. And we'll touch a little bit on that talk as well. So when it comes to value statistics acquisition, what we did was actually to add what we call a value frequency table to the L3 cache. And that mechanism monitors, first of all, the miss traffic. So when you bring in a block into the cache, then you need to update the value frequencies. And you do that by actually visiting each of the words and the values in the cache block. And then you have a table with, you index the table, you could say, with which is a cache structure, with the value. And then you have a counter to implement the counter to see a new um, another of the same value that you have stored once again. Likewise, when you evict the block, you have to also adjust the value frequency information in the value frequency table by actually going through all the values and decrement the counter itself, right? So this would be the exact way of capturing the value frequency. And it actually seemed to work quite well. So with this VFT, we can establish the frequency, and that is what is needed to do Huffman coding, okay? In fact, my traditional Huffman joke is the following. You know, in science, we need to be very careful with giving credit to the right people. And I don't think it was Huffman who came up with Huffman coding. I'm from Scandinavia. My ancestors were Vikings. Vikings were sailing with what bad people are doing from the Mediterranean area. But one thing that Vikings came across was that we encode important concepts with a single letter. For instance, island in Swedish is the letter Ö, which is the O with two dots, okay? A single letter. Because the Vikings knew, oh, there is an Ö, okay? The other concept for a river is also single letter. It's an O, it's an A with a circle on top. So they were really doing Huffman coding at that time, 1,000 years ago. Okay, and parentheses, continuing with the talk. Okay, so that I talked about. So let's see how much we can gain with Huffman coding. What we see here on the y-axis is the compression ratio. Compression ratio is defined as the size of the uncompressed object divided by the compressed object. Okay, and so compression ratio of 2 would be that we cut the size by a factor of 2. Okay? And here we see the state-of-the-art schemes FPC and VDI and SC2. And as far as SC2, we can see that the red bars are substantially higher than of FPC, the green and the blue one. So if we look at the geometric mean, we almost hit a factor of 2 in compression ratio, whereas FPC and VDI only achieve 1.5. So that was pretty, we were very happy about that. Now, as I said, one bad thing with statistical based compression is that you might need to, the value frequencies may change, okay? And we were, of course, concerned about that because you cannot afford to change the encoding that often. So we ran our benchmark for pretty much 1 second, okay? So 1,000 million committed instructions is about 7 execution, okay? And monitor the compression ratio. Here is, for example, the HMMBR benchmark. And if we look at the other ones, you can see that it's pretty flat, okay? Saying that compression ratio doesn't change. In fact, there is a funny application that's GCC, which actually can gain compression rate. Very funny behavior, actually. And it's because it enters a new phase that, for some reason, can benefit from statistical compression. So overall, we could see that, I mean, the value frequency doesn't change at all. Meaning that if we design the scheme in such a way that you can change the encoding, but you cannot afford to make it happen. It pretty much can happen in the background, but it's you cannot afford to have it happen quite often. That will performance overhead. Good. Then, of course, we wanted to see, yeah, well, so what you need to change when it comes to, I'm not going to talk too much about the cache architecture. I have to change that, but one thing that is needed is more tags, because now you can basically fill the cache with more blocks, okay? And so you need more tags. That's one additional cost, you could say. But tags, of course, consume memory, but the good thing is that compression gives you more space than the tags, okay? Compression aware replacement. You also need to make the replacement compression aware. And in fact, there are interesting open problems still in that. And then you need fast compression. And we managed to do this Huffman coding in only 4 nanoseconds per block. We did a lot of work, even down at the RTL level, to convince ourselves that our compressors and the compressors were fast enough. Giving an example of where it really makes sense, as you do a lot here at PSC, we look at from the architecture point down to very important. Some studies, you cannot just, be credible if you don't do it all the way over. So we had to do that. Okay, so what's the performance gain here? Well, what we looked at here is a number of systems. So LLC, the baseline LLC is essentially has a certain size, 4 megabytes, yeah, right. And then LLC times 2 is twice as big LLC. LLC times 4 is 4 times as big LLC. And then we have the FPC, BDI, and the SC2, okay? 4x means that it has 4 times more tags, okay? And then we looked at different workload mixes. And one of the takeaways here is that if we compare the LLC4 with SC2, you can see that you consistently get higher performance from SC2, which means the baseline with SC2 compared to 4 times bigger cache. And one can ask, why is that possible? Well, when you build a bigger cache, it will be slower, right? So you will actually lose performance when you go to a large cache. Of course, you gain performance too, because you can cut down on the miss rate, but the hit time will be longer. So, and because our decompression latency is so short, we could actually afford to have higher performance. What is also a true result is what we call a worst case here. So what we modeled now was actually all the bad things with compression. We always charge the decompression latency, but we don't take advantage of that to get a bigger cache. And the only thing that happens is that we lose a little bit of performance. It's like, you can see it's 0.9 to 1. That's only 0.1, right? 0.9 to 1 is only 0.1. So we lose about 2% of performance. That's all. In the absolutely worst case. So we were super happy about this effect. Okay, let's move on. Then something that I wanted to bring up, it's called the Python, because paper that we published in March 2015. You might wonder, why do I talk about these things? Well, it turns out that part of the results here is super relevant for large language models, okay? I'm going to get back to that in a bit later. One of the problems we addressed in that paper was actually to supporting a single compression method can make compression applicable for different data types. So what we came up with was number 1, that's why it's called hybrid compression, where you could say, a number of different compression techniques. for different types of data. I think of floating point data, you could think of pointers, you could think of integers in general, for different kind of compression methods. And then the idea is to do data type prediction, or is it type and actually pick the best one. But what I really wanted to make a point of is what we call a semantic field compression method. That so think of how you would compress floating point data. We just take the whole floating point number. It is quite, you know, a random. We're going to look at this a little bit more in detail. But if you look at the semantic fields, exponent and mantissa, then you can start to get a lot of value redundancy. Notice a lot of value redundancy, so that compression will work quite well. I'm not going to talk about the hybrid part, but I'm more willing to talk about this the floating point scheme that we came up with as one part of the paper. And here is actually, you know, floating point number subdivided into these semantic fields. And if you were to exponent is quite intuitive that you would get a lot of compression going, because again, my favorite, if you simulate physical systems like that, I said temperature in the ocean, it's going to have the same exponent, very likely, right? You can get a lot of compression going in the exponent. Unfortunately, the exponent doesn't have so many bits, okay? So that would be quite low limit on the compressibility. But if you could get some compression going in the mantissa bits, then you might be more successful. And looking at the whole mantissa is not a good idea. But if you take the most significant mantissa bits, they are likely going to stay similar. Again, you know, the temperatures not going to change more than in the decimals in the significant bits, right, on the floating point number. So we could actually apply compression separately to what we call mantissa, an exponent to mantissa high, and maybe also mantissa low, although it's not likely that to find much. This is what we did in this paper. What also can make sense is actually that we fold in the side. In fact, what has happened with floating point numbers these days, as you probably are very aware of, is that one considers, especially in machine learning, smaller and smaller floating point formats, okay? And so it's very important to do this kind of compression. Okay. What did I want to show here? Well, I'm not going to go into the details of this, but what they show is actually that if you take a number of compression schemes, we looked at ZCA, which stands for compression scheme that's very simple and only go after 0 values. And then we have the BDI, which I've talked about, SC2 I also talked about, and FBH, which is this floating point scheme that we came up with the semantic fields. Then if you look at the details here in the graphs, you will see that there is no single best scheme for benchmark. So HighCom, as we proposed in this paper, picks the best scheme out of these. We came up with heuristics to predict the data type, okay, and then you could do a very good job there. All right, this brings me to the latest, to the last sample. So I'm going to do this quite fast because I want to talk a little bit about the company. GBDI. So BDI I introduced. You have the base. You look at the cash flow for Mendelsohn, right? You take the first value as the base, and then you encode the rest as the delta. Okay, very simple scheme that works. Surprisingly well. But the thing is that one can do much better by actually not restricting picking the base from within a memory block, but really across memory block. So we came with an eye towards data analysis, statistical compression. So we wanted to find better ways of picking the base values. Let me explain this figure, okay? So here we looked at, this is just an example application, but it generalizes to quite many application cases. What we do is actually look at the values here. Here the values are in floating point format, and here they are in integers on the rightmost y-axis, and you have consecutive blocks here. And if we look at one block, then you will see that, oh, there is actually not much difference if you look at floating point numbers, just from minus 0.5 to minus 2. But the way PDI works is that it looks at integers, and then it's actually very different things. -5 times, well, actually the value space here is from 10 to the power of 9 to -2 times 10 to the power of 9. So that's a huge difference in values. Now, what we see horizontally here is that if we were to pick base values across blocks instead, there are not that many, right? So you have pretty much values concentrated around a few base values, okay? So that will speak in favor of doing clustering, okay? If you look at, if you afford to do like what we did with half criteria, to do first data analysis and do clustering, then you could afford to pick these base values, not inside a memory block, but across memory block. So we actually looked into this one, and with the goal of saving bandwidth. This was work done between Chalmers and ZeroPoint Technologies. It's not a company I'm going to talk about in a while. And in ZeroPoint Technology, the product we were working on at this time, this paper from published in APC 2022. Then actually the IP block that ZeroPoint offers is here called Septillion, and it sits integrated with the memory portfolio, say. And if we look inside if we look inside that IP block, what we have is I'm going to explain exactly what happens. So for example, if you have a miss from the last level cache, it will be intercepted by this IP block. And following the numbers, the first thing that will happen is that we look up in a prefetch buffer if that block is there. I'm going to comment on that in a while. And let's assume that it's not there. Then what we do is that we need to do address translation. Address translation is needed in compressed memory hierarchy because blocks are not fixed size anymore. They actually can, so you cannot get directly apply physical address to the memory. You need to do an address translated from a physical address to compressed addresses. So that's the purpose of the address translation. Then we go to memory. We know the location of the block and we need to pick it up, and then it will be decompressed. Now, in order to save bandwidth, we will get, if we compress, we could actually, when we pick up a 64-byte block from memory, that could actually, since data is compressed, that will correspond to multiple blocks, okay? And so we will decompress all these compressed blocks and send the requested block back to the L3, of course, but also put in the prefetch buffer the blocks that have been decompressed by not used. Okay, that's how this IP block works. Okay, I don't have time to, so we sorted out how you build a compressor and decompressor with this global basis. I don't have time to go through that. But this was, again, very important, was to really sort out exactly at the OTL level how fast we could do compression, decompression. And as we could see here, they were done in 12 and 9 stages, respectively, assuming a 1.6 gigahertz total 7 nanometer technology. So that's quite okay. To summarize the performance results, we managed to get higher compression ratio for GPDI. In fact, compresses are 2.3 times, whereas PDI and BPC, which is bit-length compression, with fairly new technique from the University of Technology, compress up to a factor of 1.6. And we could reduce traffic. The bottom line here is that we could save 50% of the traffic. It's very good. And we could see that the reduced traffic resulted in an improvement of performance. So that's it. And I have to, because we have She in the room here. It's working for you these days. But we also continue to work on compression. And here is, I don't have time to talk about it, but we had one paper in National Professor Supercomputing in 2024, and an upcoming paper in IPVPS for compression. So if you're interested, you could look into this paper. Okay? Now, this has a lot of commercial value, obviously. So I'm going to talk a little bit and finish up my talk. I'm actually done with my 25 minutes. So, ZeroPoint Technology. We founded ZeroPoint Technologies back in 2015. We have been around for a little bit more than 10 years. And it was me and
We have time, so give you 10 minutes, you can do the 10 minutes.
5 minutes.
Oh, I guess.
And then I will have enough. ZeroPoint Technology was founded by myself and Angelo Saralatos. Was author of most of the papers that we looked at. With the aim of deploying this technology. And the business model here is to offer IP growth, okay? So getting customers of basically computer vendors you can think of. They'll talk to pretty much everybody on the planet to buy and license essentially the technology integrated in that product. We have an interesting tagline: remove the waste, release the power. Where the waste is actually value redundancy in the memory. We don't need, as I started off, think about it, only to have one value, each unique value stored once, then we would reduce all the waste. That's actually a funny explanation behind ZeroPoint. So a colleague of mine said, "Oh, why don't you call yourself ZeroPoint?" Because said ZeroPoint is like bringing the information entropy to the 0 point. And I'm not good at information theory, so I bought his explanation. He said, this is a great name, ZeroPoint. Then after a while, I looked up what the information theory says about entropy. And it's the other way around. When you remove all the redundancy, then the entropy goes up. Right? 0 point. Then I twisted it a little bit and said, 0 point, the point is to remove all, to get the waste or the value redundancy to the 0 point. Yeah. All right. Let me talk a little bit. So what we have innovated over the years, we have been super ambitious to file patents. We have patents in these 3 domains, obviously in data compression algorithms, where we do significant example of what has been done in the open literature, which we are totally on top of. But very importantly, compression algorithm for the memory hierarchy should be compressed as much as possible, but also be fast, right? It needs to operate in the nanosecond scale, okay? But that's not enough. We also need to do data compaction. So what happens is if you compress one block here and another block here, then you will have small patches of freed up memory, but you need to pack it, okay, in order to realize a bigger region of freed up memory. So that's what we do, and this also has to happen at the nanosecond scale, okay? And then finally, in order to offer higher memory capacity, we need to be able to free up pages of memory. That's what the operating system would like to have. Very importantly, we don't touch the operating system. We don't touch virtual memory management. We do this totally transparently under the cover, okay? We have drivers that basically we signal, here you have some more memory, okay? So that's in a nutshell the technology, okay? And we have basically offered, we have potential products across the entire hierarchy. What is ready to, sitting on the shelf, ready to go, is essentially memory expansion technology. We have one product called GensMem, which is actually a way to cut the total cost of ownership of data centers by offering a level of the memory that is compressed, right? Using what is called CXL switches. CXL switches are there to actually expand the memory, because what has happened is that you have run out of possibility to add more DRAM to the chip itself. So you have to expand memory through CXL. The other product that I'm going to talk a little bit about is actually AI memory expansion. And let's go to that one. So basically what we have is a product that actually makes it possible to expand the capacity of high bandwidth memory. And it does so by actually we compress the data as we are after the training phase, okay? For example, the weights. And then we, at runtime, we decompress the data with an IP box that is sitting between the HBM controller and the internal SRAM in the accelerator, okay? And we do this losslessly. So in machine learning, you do a lot of compression anyway, with the pruning and the quantization. We were very surprised that when we used our proprietary algorithms, we could do lossless compression on top of this already compressed data. And believe it or not, by a factor of 1.5, we could losslessly compress the data. So this product is basically being deployed. We have a lot of interest from industry. Obviously, everybody's speaking AI these days. So that's about it. To look a little bit about how it performs. So what people are very interested in using is leaf sample 4, which is a fast variation of level C. I said seed level on level C. Anyway, but sorry, it works on, okay, works on 64 KB blocks, unlike our proprietary algorithms that actually compress on the block level, okay? I should actually, I'm done very soon. So we have, so we have so LC4 in this case didn't do much, but with set standard, which is another industry standard for compression, unfortunately, it's software algorithm. Did a lot of compression, but it's very slow. Okay, you cannot deploy it the way we do with putting it close to the controller would kill the performance. Whereas our lossless techniques, the proprietary algorithm from ZeroPoint, does very well with 1.5. And in fact, we actually also established the upper bound and lossless compression, and we're very close to that. So we're very proud of this technology. Okay, that brings me to the end. So I can try to summarize the research I've done over so many years together with my many PhD students. One of them is sitting here, soon to be doctor. I think this is a fun topic to work with. There's still, open interesting work, and I hope we're going to see it deployed soon. So that's it. Thank you very much. Question.
Do we have time for some questions? Who wants to go first or in the Zoom?
Hello, may I ask you a question?
Please go ahead.
This is Roberto.
Hey, Roberto.
Nice
Hey.
to see you. Very nice talk and very nice path to innovation. Congratulations for the success.
Thank you.
Very good. Just some curiosity. So you have this technology which compress in the cache, some compress in the RAM, and some may compress also in the interconnects in the disaggregated memory. So did you try to combine all of them?
Oh, yeah.
It's
Good
useful.
question.
The question is.
Yeah. So let me repeat the question here to the rest of the audience. So Roberto is asking, you talked about memory compression in isolation, then cache compression in isolation, and then also interconnect compression in isolation. And Roberto's a very good question was, can you combine all of these? And you can. You could think of actually having data compressed in the memory, bring it into the last level cache, not the L1 and L2, I don't think so. Then you have to have very fast decompression. But bring it in compressed mode into the cache, okay? So you decompress it first when you access the data in the last level cache. And that would give you all the values with, more memory capacity, more effective memory bandwidth, and more cache capacity. In fact, we have taken this. This is just we have submitted a patent on it, but it's definitely not in the product yet. But I took it to the extreme to have data compressed all the way to the inside the processor. To decompress it just when you need to do calculations on the data. And that's actually possible if you have fairly efficient compression algorithms, you could make it part of the pipeline. Obviously, for accelerators that are throughput oriented, it works really, really fine. But even if you're a little bit latency sensitive, you can afford to put it into the pipeline and have a pipeline functional unit that as a part of the thing you do decompression, you do the compute, you compress again, and then you ship it on. Okay. I hope that answered your question, Roberto.
Yes. So you continue to get advantage if you combine compression at many levels. That's your
Yeah.
That's good. Very good. Thank you.
Yeah. Other questions?
In one of the first papers that you spoke today, you were mentioning that the decompression or compression, I don't remember, it was taking like 4 nanoseconds. How can you measure this? Like you build the real hardware? Or...
Oh yeah, exactly. So we did all the way down to hotel. We didn't do test chips of it.
Okay.
We did hotel level simulation and could look at the latency effects. Yeah. very importantly to do it all the way down to Altela, otherwise we wouldn't know, right? And then the whole value could be gone. I mean, it could be unrealistic. Yeah. Yeah.
Hi, this is the first time that I hear something about this one.
Really?
Because my expertise is not place of memory therapy. So I wanted to ask you, not that technical question. What is the current implementation of these algorithms by ZeroPoint on that where we are?
Right. So I when it comes to AI MX, it's essentially we have it ready as an IP block that can sit between the HBM memory controller and the SRAM. So it's like a piece of hardware that you stick into your design. That's what we offer to customers essentially. When it comes to the DenseMem product, which actually goes into CXL, it's also an IP block, but it sits in a CXL switch, okay? But in both cases, I mean, the business model we're using is IP blocks that we sell as a license. We license out to customers.
Okay, do we have any example of assisting errors or that are using the technology that you license?
Sorry?
Do we have any example
Sample.
of CPUs, for example, that are implementing the product that you license, the algorithms?
So you mean a real product that incorporates this technology? That's what you're asking? So if there is a processor in the market that uses
Not yet.
So I was wondering, could you use this kind of technology also near storage to do this kind of compression?
We have actually looked at that. It was on one of the slides to do storage compression. Yes. Yeah.
Okay, but you don't have a product, or you have looked at it?
We
but-
don't have ready to go product, but very close to, I would say. Because
Okay.
I mean, we have basically what you need is the compression and decompression accelerators.
Mhm.
And we have those already, but of course, I mean, making a product, you still have, you know, a number of things you need to package it in a way to conform to interfaces and stuff like that. That we probably don't have, but I mean, the important and the difficult part we have implemented already to make it possible to do storage compression.
Because IBM and other companies, they use some FPGAs to do this kind of processing near memory or near storage. So I was wondering, because if you want to license the IP and integrate in a memory controller, this is very complex. But if you have it instantiated in an FPGA that is
But
not,
we don't integrate it into the memory controller. It's
Well,
sitting along.
yeah, but you have to go to the silicon. The silicon needs this IP in the end. No?
Sure, yes.
Yeah. If you have it in an external FPGA,
Oh,
then it's
okay, I
easier
see what you
to-
mean. Yeah,
yes.
exactly.
as I demonstrated.
No, I mean, to tell you the truth, it's not the easiest way of building a startup to do IP blocks that are sitting on a computer chip.
Yeah.
In fact, the way it started was we had done this work on, so I talked about statistical cache compression. With Angelos and myself, we looked at cache compression. And then we were in the position of creating a business around this. And I directly said it's not going to be cache compression, because how can you convince Intel and all the other big companies to say, throw out their cache and bring in our cache? It's not going to happen, right? So I said we were going to do memory compression, because then we could package it as an IP block that is fairly independent of the customer's technology. And it seemed to work, but it's the big problems with this is that I mean, a customer will not buy your thing until you have proven that it works.
Mhm.
Now, can you prove that it works unless you don't have a customer? So it's
Yeah.
like a catch-22 situation. So it's not the easiest way of getting a startup to fly, but we hope we're going to manage to do that likely within 1 and 2 years. We're going to be done. Someone is going to buy the company most likely.
So what else was to-
Hopefully, a European company that is going to save European, independence of the other continents out there. No continent mentioned.
Good. So I think there was a question.
Question. I do not have the fundamental understanding of memory compression.
Uh-huh.
So if I have understood correctly, so when you compress the data and put it in cache, like cache compression you mentioned, while computing the data on the processor, is it decompressed? No, the processor works on the,
It works on uncompressed data. Yeah.
and then
So you need to, when you access the data in the cache, which is compressed, you need to decompress it first. Yeah. Right.
Okay, so I think we are a little bit over time, so if you don't mind, we should stop here. Per will be here until the end of the day, so if someone wants to talk to him, please let me know and we'll try to schedule. He has a busy agenda, but I guess we can
Squeeze in. Yeah.
accommodate some extra meetings
Sure.
if someone is interested. So please let me know, and let's thank again Per for the presentation.
Thank you very much.
what about to ask you?